Okay. Okay, Cup. Welcome to class 8, which is the last class of the summer pre-course interactive mathematics with Mathematica. Now, last year we had again, same here, 8 lectures, but the 9th class or the 9th spot would be reserved for exam. So Wednesday is your sort of exam taking thing. So that's just to check your knowledge and understanding. Anyway, so what's on the agenda today? Hopefully we'll get to have some time for you to discuss the demonstration project that you picked out for your study. And I can elaborate on what's going on behind the scene and how you can sort of leverage it for your own project design or prototype or whatever. Okay. Now, today I'm going to talk, give you sort of intuitive or I guess intuition about what it means to do probabilistic modeling. Normally we can, in a lot of class, you can actually start maybe probability and statistics before calculus. But the way I kind of sneak this behind calculus is because of one reason, okay? And that reason is this picture. Let me go to the picture side of thing. Okay, where's my pen? Okay. So let's go to an empty screen. Right, okay. So for the last class or two, we've been talking about how we can do this thing where, you have a function here, and this represents some kind of rate of change over, say, time, okay? So this is some kind of velocity or speed, right? And if you want to multiply speed times time, but you want to do it not like in a rectangle thing, you want to do it just tiny bit at a time, so you get precise accumulation of distance. Okay, that becomes the integration, right? So we say that the distance travel, x, right? Distance travel from A to B, right? That distance is the integral of this function Vt dt from A to B. Okay. So that kind of accumulates this distance. Okay. Right? Now, the reason I want to discuss probability and statistics after this picture is clear in your head is because in probability and statistics, you also have this kind of cumulative, okay? Except instead of having this function, okay, being velocity, and you integrate velocity to get distance. So velocity times times give you distance, and you integrate. What you would have is similar kind of function, right? Also positive, but this function is special in the sense that, first of all, it cannot be negative, right? Whereas with velocity, you can actually go backward, right? You can have negative velocity. So we have this special function here. Say, let's say it looks like this. Okay, function looks like this. The idea is once you have this function, you can also do integration, but the meaning is different. Instead of having this being, say, distribution, sort of like a variation of speed over time, this is kind of like variation in likelihood over space. So think of this as some kind of space. Okay, think of this as some kind of space. And instead of having velocity over space, I have this function that sort of gives the likelihood that you will find something at that space. So if you think of this as one-dimensional space, right? One-dimensional space. And I'm kind of like tossing a pen or a dart, just randomly at this space, right? What this represents is that I'm a lot more likelihood, am more likely to find the point along here than here, more along here than here. So when I toss a point, okay, toss a dot. By the way, this is one dimension, right? It's going to be a lot over here. Oops. Yeah, can you see that? It's a lot over here, a lot here, quite a bit here as well, but not as much as here, but not so much here, and never there. So this is sort of like a probabilistic thing. It's a game thing. It's something that's not certain. Okay, but what is certain? What is certain is that likelihood there. Now, once you have this, because you know calculus, you can always find the area between here and here, right? Right? You can also find area between here and here. Okay? Now, let me ask you, what is the total possibility? In this case, this is the total possibility. It cannot be beyond this here. It cannot go to the left. It cannot go to the right. So all the possibility is in here. Okay, it's bounded to be in here. It has to be in here somewhere. So what happened is, if I can describe that it's likely to be around here, it's likely to be around here. Okay. On the other hand, if I do another picture and I draw it like this, okay, same possibility, but I draw it like this. What are you gonna say? You also will have possibility bounded within this left hand and right hand side, right? But it's more likely to be here. So I'm drawing this invisible point, okay? So all the points are going to be gathered about here. So think of this as some kind of experiment. So it's not like what we did before, right? We kind of marched from left to right. We marched from left to right. That's like time, evolution of time, and you have velocity curve over it, and you multiply velocity by time, but you do it in an instantaneous thing. That's what calculus integration gives you, total distance. Instead of accumulating distance here, you sort of like accumulating probability of catching the points. Okay, so think of this as the likelihood that this grain of sand is going to land here. So if you want to think of it this way, forget about sand. Let's think of rain. Okay, if this were to be the distribution or the likelihood of rainfall at a given point, okay, for a given hour or minute, where are you going to catch the most rain? Well, you're going to be catching the most rain here, right? Right? Intuitively, that's it. That's all there is. So I want you to take the leap from thinking about integration as accumulating distance over time. Now we are accumulating probability over space. Okay, so make that thought first. Make that thought in your head. Now, obviously, you can do the same thing, right? Right? You can say that from here to here, you have this probability. From here to here, you have that probability. So that's a lot more, right? So if you're standing here and you're standing here, you're probably going to get a lot wetter than your friends over time, because that's, rains like to be here. So chances are there's big cloud over here. Whereas if I were to draw this picture, the cloud would look a little bit like this, right? A lot here, also a lot here, but not so much here, and so forth. So that's the picture I want you guys to go with. So we go from accumulating distance as we go forward in time from left to right. Now there's no direction, right? Left to right, it's just north, south, east, west. There's no, you don't start from east to go west, or you don't start from west to go east. It's just a span. It's just a static span of distance. That's it. So I want you to think of this picture, right? So just as you can do integration here, you can do integration here, with one exception. And the exception was, two exceptions. It can't be negative, because probability cannot go negative. And when you say probability, it's a relative thing. So you might as well say something like this. If something cannot happen, it has 0 probability. If something must happen, it has 100% probability, right? So in other words, you normalize the maximum to 1. That is just a convention. Okay, that's just a convention. I can say the maximum probability is 275. Okay, but nobody would talk to me because that's kind of weird. So universally, we agree on the whole planet that if something is certain, we say that it has probability of 100%. So because I am certain, 100% certain, the rain is going to drop somewhere from here to here. And this is how I add up the probability. Okay. Obviously, what is the total area under all the curve? The total area is 100% or 100 over 100 or 1. So the difference between this general function and this function that I want to talk about is, and let me go, okay. Oops. Okay. Whereas here, you can have any function. Over here, I have this function, f. Okay. Now, to emphasize that we're not moving across time, we're moving across distance, I usually would just use x. Now, f of x is always greater than or equal to 0. That's one stipulation, right? That's common sense, right? And the other thing is, if I integrate from leftmost to rightmost, f of x dx, this function has equal to 1. Okay, so you got the concept of calculus of integration. Now I want to switch gear and say, let's focus on particular kind of function that allows you to integrate the same way before, except by convention, this function cannot be negative because I want to interpret it as probability of encountering something. I can have 0 probability. I cannot go lower. And the total, the maximum, you cannot be, you know, in sort of like commercial, you can say 1,000% sure. You cannot be 1,000% sure. You can only be 100% sure. That's as high as it gets. Because of that, that's the convention. Everybody all over the world agree the maximum certainty is 100%. The certainty is somewhere in here, right? So it has to be in here. You don't know if it's going to be here or here, but you know that, let's say it's going to be between these 2 points. So when you integrate all the area, that area has to be 1. Okay. Now, the way I drew it, this A and B is a fixed point in space. Something like, say, this A is equal to 1 and B is equal to 7.5 or something like that. Okay. It's just a real number. It's a real number. But guess what? In mathematics, these 2 conditions allows me to do something else. I don't have to have a real limit here. I can actually have some function that goes on to infinity. Okay. Now, conceivably, that's sort of like, oh, that's pretty far, right? You're going up to infinity. But conceptually, if you have something that goes to infinity, as long as the area is 1, you're not violating any game. Okay. So that's the rule of the game today. That's the rule of the game today. Okay. So if you agree with me that we are going to focus on the nature of function that doesn't go negative, function that if you integrate all the area under that curve, it will be exactly 1 by definition. Okay, by definition. Okay. So think of this thing in mind. Think of this thing in mind. Okay. Now, so have that tucked in the back of your mind, okay? The concept that you have something that's non-negative and you add the area and it's 1. Okay. Now let's go back to something like a real world example. Okay. So let's say, and I'm going to do this just arbitrary. Okay. New notebook. Now you can start playing with this. Okay. Just type in the way I type, but let's say my sample is equal to random variate. Okay. Random variate, and just open bracket. Okay. Open bracket, and just say normal. Okay. Just you don't know what the meaning of it is, but just type the way you have your computer. Normal distribution. Okay. Open and close bracket, and you say something like 5,000. Okay. 5,000. Okay. So if you key this in, okay, you're going to get some numbers. In fact, this function generates this many numbers according to this rule. Okay, forget about what the rule is called. Just type the way I type it. Random variate generate this many number according to this rule. What happened is I'm going to get a whole bunch of numbers. Okay, whole bunch of numbers. Right? Now, this number can be something that you observe in nature. So this I'm sort of like imitating reality. So you run into some kind of data, and this data set, this is a real number. This is a measurement of something. This could be something like a profit and loss. Sometimes you make money, sometimes you lose money. A lot of time you don't make any money, you don't lose any money, or something like that, right? Now, let's forget. Let's say you haven't seen this. I put semicolon so you don't see it. Okay, let's visualize it. How would you visualize 500 data point? How would you visualize 500 data point? Would you write them all down in a big table and stare at it? Most likely not, right? You know this, in Excel, you have this function called a histogram or something like that, right? Okay, well, same thing. So let's do this. Histogram, my sample. Okay, my sample. Now, this. Okay, I want to emphasize, this looks just like the picture I was drawing earlier, right? In a way, if I smooth out this line, I can smooth out this line, okay? And in fact, you know, if I did this, histogram, if I make it, histogram has another parameter, like the number of bin or something like that. So if I say, make it, you know, more details, maybe. Okay. So it's gonna be a bit more detailed. Okay. Now this is not very, okay, let's make it a little bit, 5,000, maybe that's not enough. Yes, let's make it. Okay, let's make it 50,000. Okay. Now it looks really nice. Okay. This is not quite what I drew earlier, right? But it looks a little bit like it. It looks a little bit like it. Now, watch this. There are two features. Okay, there are two features that you can notice. First of all, it cannot go negative. It cannot go negative. Okay. Now, let's assume every little point is 1 millimeter tall. Okay, every single point is 1 millimeter tall. Okay. What is this volume? Well, it's 50,000 times 1 millimeter, right? Right? That's the height. Okay. So the height is not, sorry, the volume here is not 1. So it's not the same thing as what we talked about earlier, right? Earlier, I said, I have something like this. Looks very nice. And the area here is 100%. Okay, so all one. This thing it's not a function. It's got jagged edge, right? But what I'm telling you is that this thing here is called normal distribution. Okay, and that's this command here. This command say, look up this shape. Look up this shape. Okay, this shape has the center around 0 and go plus minus. This function say, look at that shape. Generate 50,000 of them. Once I generate 50,000 of them, it becomes a real number. It's no longer a random thing. It's a real value. Okay. This here, I take this thing that I generated and then make a histogram out of it. Okay. So it's just a game. I'm just making something fun. Okay. It's just something fun. Now, what I want you to know is that, and you could be taking class in probability and statistics. Okay. This is what happened in life. This thing here, I did it artificially for you guys. In reality, this one is something you get from real life. So instead of generating this becomes your data. Okay, becomes your data. Now, watch this. Once you get your data, if you want to visualize the same thing here, right? Now, except the data is not created from me. So you can imagine that this line is the work of God. God generated this number, okay? Generated 50,000 number. When you go into business, you want to measure something, your client, your whatever, you collect those numbers. Those numbers are not up to you. You collect them. It's generated from somewhere. So let's say God generated this number. You collected them. Once you collected them, you can visualize them with this histogram. Okay? Probabilistic modeling is like this. It's the opposite of the game we play. The game I play, I generate from this function a whole bunch of points. Probabilistic modeling is the opposite. You get the points first. Then you fit the point with this distribution. Okay. And you say that this is a nice fit, right? It's a nice fit, right? That thing happens to be called normal distribution. Okay, let me say that again. Okay. The game I play was that I have this function built in Mathematica. I have this function built in. I generate 50,000 of them and I get this stack of, coins or whatever, sand or whatever, okay, pebbles, okay. Probabilistic modeling, okay, again, we talked about the importance of modeling and prediction and so forth, okay. Probabilistic modeling is looking at the data first, okay, and then think of, wait a minute, this looks like a nice fit for this function, and this function is called normal distribution. Okay, let me show you how that's done. Okay, so actually the way it's done is like this. So this is assuming, so this is sort of like God's creation. God created 50,000 number, just gave it to you. Okay, you don't know where it came from. I happen to know because I created it, but you got this data set. The way you would fit is you would say, give me fine distribution of this data set, my sample. Okay, Mathematica is gonna try to find it. And this is what it returned. Watch this. It returned the word that you saw before. Okay, you remember this word, right? Because actually it's consistent, right? I use this function to generate. So when I ask the computer to find it, it finds the original function. So it's got this thing. But look, it comes up with some other number here. Okay, well, what I did was I used what's called a default setting. Okay, think of it as two buttons, two tweaks. One button I set to 0 and one button I set to 1. So when the computer tried to find the fit, because there's some kind of randomness, it's got the right name. It's got the right name, normal distribution, but the tweak button is not quite correct. It's very close. It's not 0 and 1. It is 0.024557, whatever. Okay, it's very close. It's very close. Now, let me try something else. Let me go back and I just say, I want to generate just 50 of them. Now 500. If I generate 500 of them, okay, look at the histogram. It's not very nice. It's not very smooth. So if I were given this many data, right, I'm going to say, well, maybe it's like this, or maybe it's like that, or like this. I'm not quite sure. I'm not quite certain. It's not very, it doesn't give you a nice, definite meaning, but that definite assurance that you're going to get the right number. Okay. And in fact, if I do this fine distribution, it gives something even worse. Even, you know, the accuracy is even gone down. So that's kind of like a natural way to think. Now, so this gets back to the heart of what it means to do probabilistic modeling. Okay. So I can maybe write it as a note if I like. Okay. So this is your job. You get some kind of data. You get a set of numbers called comprising, say, n numbers. Okay. You visualize it with histogram. And then you try to guess which function was used to generate it. Okay. That is probability modeling. Now, I told you, right, that probability modeling of any kind is what gives you ability to predict. Okay. So what prediction did you do? What is the prediction that you, what prediction can you make when you have this? Okay. Once you have this function, okay, once you have this function, let's say this is, I don't know, this is a center of July or something like that, right? All right. My question to you is, where should you go to collect the most rain? Where? Well, you would be here, right? To collect the most rain. Okay. What else? What if you ask the other question? Instead of saying, where do I get the most rain? You say, my friend is standing 2 kilometers from the center of July. Okay, 2 kilometers. And between 2 kilometers and 3 kilometers, that's between 2 and 3 kilometers from the center of July. What is the probability of getting wet? It's this area, right? Compared to the whole, right? So this is you can think of this in two ways. You can think of it as, of the thousands and thousands of raindrops, you're going to collect them like this. Or you can think of it as the probability, once you get this red line, it's the probability of a single drop of rain. Okay. So when I asked you earlier, where are you likely to get rain? Well, you're most likely to get wet here. Okay. Right. So you're most likely to get wet here, but your friend who's somewhere between 2 and 3 kilometers, the probability of him getting rain is, anybody? The whole area. Now this is not normalized, but I'm going to normalize this to so that the area is 1. So the area is 100%. And then between 2 and 3 kilometers, what is the probability of getting wet? It's simply the area under the curve. So calculus comes in. So even though you don't want to do calculus, it's part of probability. Okay. So what's the probability of getting wet? It's integral from 2 to 3 dx of this function f of x, where this function is called normal distribution. Okay. So if you didn't know any better, you wouldn't be able to predict where it's going to rain, right? So that's what, I guess, you can think of weather forecast. Okay. So this is a kind of like a predicting where it's going to rain. So you're most likely going to get wet here. You're not so much likely to get wet here. That's it. That's all probabilistic modeling is all about. Okay. Last week, okay, I told you that. Let's go to last week. Okay. Last week in this class, it's there. Humans, we go to this one here. So probabilistic model. Y is a probabilistic statement. Okay. X is some, input. So what is your Y here? Your Y would be something like, given some information, past rainfall, reading of your thermometer, barometer, whatever, you are going to give exactly the probability that it's going to rain between this point and that point. That's your prediction. And that's exactly how you get, you go to your app. Okay, go to your app and you go to weather app and it say Bangkok, right? Tomorrow, Bangkok, 70%. What it means is this. This is one dimension, so it's not quite right, but let's say the country of Thailand is one dimensional. Okay. There's a probability of rainfall over the kingdom of Thailand. And from here to here is Bangkok. And the area under that curve. Okay. Now, this is not strictly quite true interpretation of how they make the prediction. Okay. But it's more like this. It's more like I don't have a coin. Okay. You guys have a coin, right? You have a coin. Okay. So if I want to go back to something even simpler, okay, what is the simplest form of randomness you know? Coin toss, right? Coin toss. Now, what's the difference between coin toss and this kind of elaborate, where is it going to rain thing? Well, the coin can land anywhere, so that's quite complex as well, right? The thing is, you don't care. You don't care about the infinite possibility of location. You only care about head or tail. Okay? So I'm going to draw another picture. And this one is actually the picture that most probability class starts out with. And that's a picture of a coin toss. Okay? With a coin toss, it looks exactly like this. If, first of all, I have to say the coin has head or tail, right? Okay. So I have to give you probability of head and probability of tail. I can do that on a table. Can I do it on a graph? Now, this is trickier than you think. You cannot. Okay? You cannot. You cannot draw head and tail on a graph because there's no meaning of H. There's no meaning of T on a graph. What you have to do is you have to do one step in between. You have to say H correspond to 0 and T correspond to 1. Now you're in the game. Okay? Now you can do this. This is 0 and this is 1. Okay? Now, I can redraw this. If I were to draw something like this before, would it make sense? Anybody? No, because apparently if I did this, watch my hand. Because my hand is sort of like here between 0 and 1, right? I can say, I can integrate the probability, and there's a probability that the coin will land between 0.5 and 0.7. Okay, is that valid? That's not valid because I only allow 2 values. So I have to start over. So basically the function I have, if H and T maps into 0 and 1. By the way, I can also make 1 and 0. Okay, it doesn't matter, of 5 and 7. Why are you guys walking in and out so much? Huh? ให้เพื่อนแล้วเพื่อนรอไม่ได้เหรอลูก โอเคเด็กไม่เคยไปเมืองนอก Right. Okay. You have 0 and 1. Okay. You have 0 and 1. Now, instead of having this kind of blurry probability, I have to concentrate probability. It can only be 2 values. Okay. So I no longer have this kind of blurry function that I can integrate. Okay. I'm going to make it a spike. So I'm going to put in just a stick and another stick. But because I want to obey the same convention, instead of saying that the integral or the area under curve adds up to 1, I'm going to say what? I'm going to say this length plus this length is equal to 1. Can I do that? Right? So it's different concept. It's a different way of looking at the graph. Okay?หนูไม่ต้องอยู่ก็ได้นะลูกเชิญออกเลย Okay. So instead of having something where the whole area under the curve adds to 1, I'm just going to say the length here plus this is equal to 1. Now, again, by convention, this is 1 by convention. Okay. What else is by convention? Head to 1 and tail to 0. That's also by convention. Okay, that just happened to be the way most of the textbook would work. Okay, so head to 1, tail to 0, 2 value, only 2 value, right? Instead of having the whole area integrate to 1, I'm going to make the whole length add up to 1, and that length cannot be negative. So should I make it A and B? I shouldn't actually. You know why? Because if I say it's A and B, I have to say A plus B is equal to 1. So again, this is by convention. I put this as P. And if this is P and sum of this is 1, what is the height? of this guy. It's 1 minus p, right? Okay. So, let me start again. You have head and you have tail. Okay. You have head and tail, right? You say this is equal to 1. This corresponds to 1. This corresponds to 0. And you have a coin. Now, a coin is 50-50. You know that, right? But let's say it's not 50-50. So instead of saying 50-50, I make it p and 1 minus p at value 0 and value 1. Okay. Now let's do the same game. Okay. This one has different name. Okay. This name here is normal distribution. I can do that, right? I can do that. This thing has a different name. The name is Bernoulli. Okay. Never mind where it comes from. I'm just going to call it Bernoulli. If I ask Mathematica to generate 50,000 Bernoulli like this, okay, what is going to be the histogram? The histogram is just going to look a little bit like this, right? Except, you know, that doesn't normalize to 1. It just as many as you have points. And if I ask the computer again to do the opposite, okay, I can do that now, but just to save time, I'm not going to say it. Okay, so I generate random variate, open bracket, Bernoulli, p. Let's say p is 0.6. Okay, so I can do that. And I generate 50,000 of them. Okay, that's my data. I'm assuming I see that data in life. Now, the opposite problem is you have the data, you don't know how it's generated. You want to guess what process, what function was used to create that. Then you use fine distribution. Mathematica did that for you. Okay, but in the old days, you have to think of it yourself. And it's going to give you something like, oh, probably Bernoulli p equal to 0.59. It won't get exactly right because it's kind of like approximating from the data you get. Okay, that's exactly the name of the game. Okay, so this here. So now you know two kind of probabilistic statement. Okay, so this thing here. Now this is where I want you to memorize for the rest of your life. This here is what can you observe, or what you can see, right? Just now, when it's 0 and 1, because you can't see anything else, you can only see 0 and 1. In the bracket, 0 means head, 1 means tail, okay? So that's what you can see. Up here is the probability associated with those values. So this is the two axes you're going to see when you do probability model. Okay, your job okay, your job is, again, let's think back to Friday. You can only do better business if you can predict better. You can predict better if you have a better model, right? Your job is to build the model. Okay, the model, in this case, I show you the shortcut of how to build the model. You just go to Mathematica and say, find distribution. Okay, but you know, in 50 years ago, what I did just now would have taken an hour. Okay, so what happened is, building the model it's a bit like this, but you start from actual thing that you see. So that would be the histogram. And then you reverse the process. You say, what kind of function would have generated this? Okay, what kind of function? And that function, you know, for example, this Bernoulli has a p. So you don't just guess that it's Bernoulli. You also guess the value of p. So you have two jobs, right? You have two jobs. So I want to give you the notion of function versus parameter. Okay. ไม่ค่อยสะดวกเท่าแต่ไม่เป็นไรมั้งมันไม่มีเนาะตั้งมัน Okay, let me move this thing to me. Okay. This is like the name. You only saw two names. One is normal, okay? And let me give you right away. Throughout your career, if you know about 10 of them, you're okay. Okay? Mathematicians have derived hundreds of different functions that would give you this kind of randomness. But if you know 10 of them, only 10 of them that have ever been invented, you're good. You can fit just about any data in the that you can see, mostly. Okay? So anything else would have to go to machine learning. But any job that a statistician can be expected to do, you only need to do 10 recipe, 10 function would get you by in life. Okay, I'll tell you what those are later. But now you only saw two. One is Bernoulli, one is normal. That's like this guy. Now, with normal distribution, this is a normal distribution. So is this, right? So it's got the normal distribution gives you the shape, but it doesn't tell you where the center is. It also doesn't tell you how widespread it is. So you need two numbers. One number say, where is the center? The other one is how wide is spread. So this normal distribution requires two numbers. Those numbers are called parameter. And by convention, parameter is denoted generically with theta. Okay? So if this is normal, this theta is two number. It's like game, okay? If the game is normal, the theta is two number, and the x is the possibility. If the game is Bernoulli, okay, what can you play with? You can only play with the height, right? P. So this theta is equal to one number, P. Okay? So with that, we can go to interactive. Again, let's go to interactive. Now, watch this. Well, let's immediately go to manipulate. Why not? Manipulate. Okay, you can type along. Okay. I'm going to manipulate P. That's what I'm going to do. Because P is the one that I can play with. So I'm going to say P. P going from, say, 0.1 to 0.9. Okay, that's what I'm going to manipulate. Now, this is the function. The function is PDF. Okay, don't ask me why. It's called probability distribution function. That's why. Okay, so I want the PDF. So this is like generic. Okay, this is like function with the specification that it cannot go below this 0. And if it has this continuous shape, it has to integrate to 1. If it has a spiky shape, it has to sum up to 1. That's what this PDF means. It's a special kind of F. That's what it means. Now, that special kind of F, you know two brands. One is called Bernoulli, one is called normal. So I'm going to go Bernoulli first. Bernoulli distribution. Okay, see, once I type it and I say P. X. So let's plot this. Let's plot this. Okay, and X say 0 and 1. Oops. That comment. Come on, come on. Oh, I made it mad because I didn't put the bracket aboard. Comment. Okay. Oh, okay. Yeah. I'll tell you why it doesn't plot this later, but let's go to normal distribution. It's normal distribution. Okay. And I'm going to put in two things. One is called mean, and one is called standard deviation. And mean is between 0 and 9. And okay, I haven't told you what it is. Okay. Oh, PDF of this of x. Yeah, should work. Should work.
Where's my pen?
I have no idea why.
Where's my pen? ก็ว่าทำไมมันหายอะไรหายไปวะ Okay, Sylvia. So right now.
ไม่ลูกเวลาเพื่อนไม่มีมารยาทมันไม่ค่อยน่ารักมัน Okay, it's weird. I don't know what. Okay, let me just go to the example that I make for you. This is really weird. Okay. You know what? Let me, for some reason, I don't know why this kind of like weird. Okay, let me start this thing over and see why. Okay, let me start again. It's really weird. It shouldn't have that. Okay, seems to work all right. I don't know where that is. Okay. Right. The function I should have used was bar chart, not plot, because well, I'll tell you why later. But anyway, so this is my P. This is my P. If I make the right one higher, okay, can you guys see that? This is 0.8. So the height of the right stick is 0.8. So the height of the left stick has to be 0.2. Okay, so this is where you have this kind of binary event. This is where you have this kind of binary event. Now, when I said earlier, that we're talking about a coin toss, you guys may have no idea why would you have a coin toss that's not 50-50. Okay, so instead of coin toss, I want you to think of this. This is called a roulette. A roulette is a spinning wheel. Okay, Now, if instead of tossing a coin, I did this. In other words, I spin this thing around and I see where it lands, right? Now, I meant to draw 3/4. So what's the probability of head in this case? P is equal to 0.75, right? So in this case, it's binary like a coin, but it doesn't have to be symmetric. It can be a cheat coin. It can be a defective coin. This event, okay, is the most fundamental building block of probability theory. It's the most basic thing. Because if you think about it, all the randomness in the universe is created from adding tiny little bit of randomness. So what is the most basic randomness? So when you have two things happening, and you're not sure which is going to happen with certain probability. So this thing here, this thing is called Bernoulli P. Okay, P is that the size of the roulette relative to, so the whole thing is what, 360 angle, right? 360 degree. If I paint 270 degree of it and I call it head, what's the probability of head? Well, it's 270 degree divided by 360 degree, right? That's 3 divided by 4, so 0.75. Okay, so this angle here is 90. So tail is 90 divided by 360. So what's the probability of tail? 25, right? 25%. Okay. By the way, so this is 1, this is 2. Now, let's say I have this coin. Sorry. Oh, yeah, sorry. I have this roulette, right? I have this roulette. So let's set this at, what is it? 0.75. Okay, I get this. Okay, so this is exactly the roulette that you saw earlier that I was drawing. Okay, now let's say I make one turn. What's the probability of 1? 0.75. What's the probability of 0? 0.25. What if I did this twice and I add them up? Okay, okay, watch this, right? So if I add up 2 of these events, what are the values I can get? Instead of 0 and 1, now you have 0, 1, and 2, right? 0, 1, and 2, right? So now you have 3 possibility. You have 3 possibility. Okay? If you toss 3 times, what's your possibility? 4. You can have 0, 1, 2, and 3, right? Now, if you add this probability up, you will get something like this. So this is number of times I am doing the roulette or coin toss. If I do it 2 times, I get this. Now, why do I get that height? Anybody? Anybody want to guess? Not, you agree with me, right? If you toss 2 coins, you get 0, 1, and 2 as your possibility. The point is, where do you get the probability? Okay, this is your probability of 1. Okay. Now, if you know anything about, and this is, okay, maybe you don't know this, but I'm telling you this. Two things that are completely independent of each other, the probability of them happening is multiplied. So if probability of 1 is P, probability of 2 ones is P times P. So P squared. Okay, this is P squared. That's the probability of 2 ones. Okay. What's the probability of 2 0? 1 minus P times 1 minus P. That's the probability of 2 0. What's the probability of 1, 1, and 1 0? Anybody? 1 1 and 1 0. Well, you have two situations. You can have 1 in the beginning and 0 at the end, or you can have 0 at the beginning, 1 at the end. Okay, so you can have 1 in the beginning times 0, or you can have 0 and 1, right? By the way, you notice same thing happening, front, back, front kind of thing. That's why if you start with Bernoulli, but you do it more than once, this is called binomial. Because this front, back, front is from binomial theorem. So this binomial is n has 2 parameters. P is the probability of a single one. Okay, n is the number of times you do this independently. And x has this distribution. This curly thing means x has this shape. X, this is x. This is the distribution. X has this shape. It's the same thing as x curly binomial NP, where n is equal to 2 and p is equal to 7.5. Now, okay, so okay, anybody else want to try guess what's going to happen if I make n is equal to 3? Well, it's going to have 4 possibilities, right? What about 10? Look at this. See, it's starting to get this shape where it bulges in the middle. Why do you think that is? Because even though probability of 1 is really high, to get this thing, what is this? This is probability of 10 ones consecutively, right? So it's 0.75 times 0.75 times 0.75. So 0.75 to the power 10 is still bigger than 0.25 to the power 10, but it certainly doesn't have that many combinations. In other words, this is straight 1, 1, 1, 1, 1, 1, 1, 1, 1. Whereas here, look at this. What is this line corresponding to? It's a probability of how many ones? 8. And you have more choice of that, right? Because you can have 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0. You can also have 0, 0, 1, 1, 1, 1, 1, 1, 1, 1. And you have a few more combinations. So even though 1 and 0 together have small probability, smaller than 1 and 1, you have many combinations. And this is all from the binomial probability. That's why this is called binomial distribution. Okay. Now, I have just given you now, would you agree with me that binomial and Bernoulli are related, right? You add Bernoulli, you get binomial. So when I say the most fundamental building blocks of probability is Bernoulli, I'm going to change my mind. I'm going to say the most fundamental building block is binomial. Is that okay? I'm just adding more by Bernoulli, okay? So now you have two things. You have normal. Okay, this works when you have a continuous range of number. Then you have binomial. Binomial is where you have independent events 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, right? And you get something like this. Anybody wants to guess what happened? If I actually make this, okay, where and you don't know this, but it would make sense. As I make n very big, goes to infinity, and p goes to 0. Now that means single head has small probability. Turns out if I did this thing is gonna become so fine that it has mathematically the same shape as that. Okay, it will do that. Okay, so that tells you why you see this normal shape a lot. That's the name of the shape. It's called normal. The reason they call it normal, well, Bernoulli is named after a guy named Bernoulli. Binomial is because this front back front is called binomial theorem. This distribution should have been called Gaussian distribution because the guy who came up with it was named Gauss. The reason you don't call this distribution Gaussian is because you normally see it everywhere. So that's why I call normal distribution. Normally you see this kind of distribution. Okay, and I just show you one reason why you would see the normal distribution. One reason, because life, all the randomness, okay, think of that rainfall. Let's think of that rainfall. Think of that rainfall. Rain can happen anywhere continuously from here to here. In fact, goes to minus infinity to plus infinity, but mostly concentrated here. You can think of it this way. The rain starts at a very high, somewhere very high, right? Very high. And that raindrop runs into air particle. Okay? And that air particle either turn the raindrop to the right or to the left. Okay? And it did this so many times. Guess what's going to happen? What's the chance that the raindrop will go right? Very small. What's the chance that the raindrop is going to go left? Very small. But there's a lot of combination of right, left, right that cancel each other out. That's why most of the raindrop goes right here. So this is why, even fundamental nature, you say, raindrop has this distribution. You can think of raindrop has, left, right. It doesn't really hit air molecules, so like get blown by the wind. Okay, so a little bit of wind push it this way, a little bit wind push it that way. What's the probability that all the way down it get pushed to the right? It's going to be less, right? Because this is random. So that's why when you have the cloud over here, okay, and you don't have like a wind blowing, okay, you just have tiny disturbance. So let's say a raindrop. Okay, this one goes over here. This one go over here, 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 go over here, go over here. And if you collect all the raindrop, you get that shape. That's why mathematically, this function is named Gaussian function from the guy named Gauss. but you don't know it as Gaussian distribution. You know it as normal distribution because it happens so much in life. Okay. Now, in statistics, you have another reason why you see normal distribution a lot, but I don't want to cover that. So what is the point of today? Okay. The point of today is that I have shown you in 3 lines, in 3 steps. Okay, in 3 steps. Although I cheat a little bit, so I say, this is my data. So I generated this data. Oops, I did this, right? You saw that. But in reality, you don't generate that. You get data from somewhere. So instead of my sample, okay, is equal to random variate, say normal distribution, okay, say so 0.0. So for example, if I were to do this, this would look like a stock market of some country. Okay, this, and say 1,000. If I did this, this would be the daily return of some stock market. Okay. The point is, in reality, you don't do this yourself because you're not generating, you're not God, you're not creating the numbers. In reality, you would say, my sample is equal to import something like, set stock return data 1,000 days .csv or something like that. Okay. So that's in real life, this is what you would do. Okay. So I just now I generated this to make it looks like something we can play with, but in reality, you are not going to generate your data. You're going to get it. Okay. The point is, if this thing in a way is generated from that, when you do find distribution, my sample, you should get something like this back. Okay. Sometimes you don't hear the word probabilistic modeling. You hear the word statistical fitting. What it means is that by assuming that it's going to be a normal distribution, it's the statistics from your data that gives you the number. So that's why it's called statistical estimation. So let me summarize the step. Okay, let me summarize the step. And this is something that you're going to take with you for, I don't know, the rest of. Okay. Let's go back to here. Okay. Here, remember I told you, you have X, you want to predict Y. In this case, Y is not something else. Y is a probability of X. That's what probabilistic modeling is. Okay. Now, what are the steps of probabilistic modeling? So I can write it here if you want. Okay. So what's the step? Number 1, get the data. Look at it with histogram. Okay. Guess the shape. Okay. Guess the shape. Say the shape is normal. Then you find out what the parameter for that is. In other words, you do 2 steps. Okay. In Mathematica, it did it for you in 1 step. So you think it's a 1 step process. It's not. You guess first that it's normal distribution. And then you find out what the middle is, how wide it's spread. Same thing with Bernoulli binomial. Okay. So if I see a histogram that has 2 stacks, okay, if I see this, okay, and this is something that you can see this, okay, I happen to see in life, 1,000 data point, 1,000 data point, 1,000 data point. And this thing has 300. And this one has 700. Okay. You see this in your data. What is your guess? Are you going to guess normal? No. You're gonna guess Bernoulli. Once you guess Bernoulli, you have to guess the P. What is the best guess? Well, if it was up to me, I would guess it's probably Bernoulli 0.7, because that's the one that fits the data best, right? So get this Bernoulli picture in your head, because that's fundamentally the step you do. You get the data, you see what it looks like, right? And then you guess what the shape is. And the shape has a parameter that you have to specify. So this shape would look different if I say P is equal to 0.25. So even though you get the right family, this is called family sometimes, you get the name right, Bernoulli, but if you put in something silly over here, it's not going to be a good fit. Now, let's imagine that this is the data of the rainfall for the past 500 years in Bangkok over the summer. Your prediction is in summer, monsoon season. In monsoon season, probability of a rain on a given day is 0.7. Okay? So that's the name of the game. Now, you're going to learn a little bit of detail of how you measure the mean, the variance, and that's coming up in a lot more detail in your probability statistics class. But the point of it is the step that you saw here. That's it. That's all you do. Okay? That's all you do. Where's the Mathematica? Okay? So you see, in reality, you would see this. Okay, and you would try to draw a shape that fits its best. Okay, now, so it's always 3 steps. Okay, in reality, this step is broken down into 2. Okay, it's something like this. Instead of find distribution, it's saying, you know, it would be something like find P, assuming that we are looking at Bernoulli P, okay? And then you would say, well, find something else if it's not Bernoulli. Now, let's go to one of the most useful pages in Wikipedia. So again, this thing is this last step, okay? Mathematica is very clever. So it does it in 1 step. But in reality, it's done in 2 steps. You choose the function, choose the parameter, okay? And find the one that's best. So maybe this function and this parameter fits as good as the other function with another set of parameters that you don't know which one's better, okay? In that case, you have some other criteria like the most frequently used one, okay? Now, let me show you this, okay? So these are the 3 or 4 steps. Step 1, this is not done by you. This is done by nature. Okay, this is done by nature. And then you look at it from the histogram and then you find out what distribution is. Okay, but again, with Mathematica, you can just not do any thinking. Just say, find me a distribution. Internally, it does the loop. It fits the histogram. It checks out if it's good or not bad. Okay, but it's very high level thing. That's why it's a very good tool for those of you who are not going to programming in detail in Python. In Python, you have to do the loop, like check the distribution, find the best fit, return the goodness of fit or something like that. Whereas in Mathematica, the high level, you say, well, find the best that you can do, assuming an intelligent data scientist is working on it. Okay, now it's fine and well that you have this tool. You have to go to the toilet. Okay, go, come back. Okay, sorry. Yeah, my apology. Earlier, I couldn't I couldn't plot the discrete. The command I was supposed to use was discrete plot. So I show this to you guys. So that's the discrete. Now, so I think that's what I wanted to show. Okay, come. Jacob, welcome back from the break. Yeah, earlier I was trying to plot the distribution of Bernoulli and binomial distribution, and I couldn't because I was supposed to use the word discrete plot, not plot, because it's actually a discrete point. I kind of forgot that. But anyway, I want you to look at this. I sent this in the line, so you should have it. Okay. So what I did was that, okay, notice binomial distribution NP. Those are the parameter, right? So N is the number of coin toss or number of roulette, right? So if I did this N times, what is the highest number I can get by adding them all up? N. What's the lowest number? I get 0. So if I did this coin toss N times, each time I register a 1, I did it 27 times. The lowest number I can get is 0. The highest number I can get is 27. So that's the N. So in this case, my N is equal to 7. My N is equal to 7. My P is point something. I can show you what it is. Hold on. Let's reveal it. Yeah, 0.5. It's quite easy. So it's 0.5, right? So what's the probability of getting 1, 1? 0.5. What's the probability of getting 2 1s? 0.5 times 0.5, 0.25. What's the probability of getting 1, 1, 1? That's 0.5 times 0.5 times 0.5. Okay. What's the probability of getting 1, 1, 1, 1, 1, 1, 1 7 times consecutively? That's this. It's quite small. Okay. That is also the same probability as, because in this case it's 0.5, right? It's probability of getting 0, 0, 0, 0, 0 7 times. So this is my probability distribution. Okay. Now there's a version of this. Is called cumulative distribution function. And that's sort of like probability, instead of saying probability at a point or less than that. So instead of probability, there's the word cumulative, C. Okay, so I'm plotting both of them. Okay, so because cumulative adds up, right? It's the integration basically, right? So it has to be adding up all the way to 1. So this feature of this cumulative distribution function is it starts from 0 and somehow ends up 1. That's it. Okay? Because you know we agree, right? We agree that we once you get all the possibility, total probability has to add up to 1 and no more. That's what this is. Okay? Now, what I want you to do, okay. I gave you a wrong impression that in life, you can just have this Mathematica do fine distribution for you. You have to be more intelligent about it in the sense that even though you can, and I do this, I actually ask Mathematica to algorithmically come up with the name of the distribution. But if the name of the distribution is so esoteric and so weird, maybe I would try something that is not so strange. Remember I told you about, there are about 10 probability distribution in life that you can rely on. Well, if you go to Wikipedia, okay, you go to Wikipedia and you go to any page that has probability, say in this case, okay, Bernoulli, okay. Now this is going to give you exactly what I told you about, except it's not interactive because it's a static page. See this, Wikipedia tried to show you 3 cases. P is equal to 1, sorry, P is equal to 0.8, 0.2, and 0.5. Now, if you did this interactively, you would just come back to here. N is equal to 1, and just say 0.2. Okay, that's one picture. 0.5. That's another picture. And then 0.8. Okay. So basically, instead of this being interactive, I can do this. Okay. Whereas because Wikipedia is a static page, you only get 3 cases. Okay. So they show you 3 cases. Fine. That's not the point. Okay. And it has got all kind of detailed explanation. Okay. And yeah, it links to Jacob Bernoulli. So if you click this, you see what the guy looks like. Yeah, that's him. Okay. Anyway, the point is, for any kind of probability in a Wikipedia page, if you scroll all the way down to the bottom, and this is where practical use come in. Again, I show you the sort of like a Mathematica heuristic. You say, find me a distribution. Mathematica is going to pick you the best name distribution and then give you the parameter. In real life, you have to sort of like communicate what distribution that is. And this is why I'm saying this. There are so many distributions here. In fact, this is not the comprehensive list. Okay, mathematicians have come up with a lot more. So there are 1,000, well, let's say 500 probability function you can choose. But in Wikipedia, they separate it into groups. And this is what I want to tell you about groups. Okay, groups of function, groups of distribution function. And within each group of distribution function, some of them are more ubiquitous. So you already saw Bernoulli, binomial. There's normal in here somewhere. Normal, okay? So at the beginning of the period, I told you that there are 10 of these guys that you will get by. So let's say Mathematica gives you, okay, the best function, the best fit is, say, this guy, Maxwell-Boltzmann, okay? It's a little bit hard to explain that to your client or to your team, why you came up with the Maxwell-Boltzmann. So sometime in practical use, you would go to the same group, but find the one that's more familiar. Does that make sense? This is sort of like practical tools of the trade, you know, as a consultancy. So even though I know the best fit for this data set turns out to be, you know, poly-Weibull, okay? If I communicate that to my client, they're going to get, you know, they're just going to get lost. But if I tell them, actually, it's this thing, it's gamma. Well, gamma is not familiar to you, but to a lot of business people, they're familiar with gamma. They're certainly not familiar with Maxwell-Boltzmann. They're not familiar with Maxwell-Junter, okay? So this is sort of like my tricks a little bit. So again, Mathematica can find the best fit, but you have to choose the one that is kind of like popular. Think of it like it's a brand name, yeah? Think of it as a brand name. So within each groups, there are kind of brand name that your client will be familiar with, okay? And I told you that in life, if you know 10 brands from this list, you're good. You're good, okay? Now, the key idea is I have to tell you that how is this group organized? Okay. How is this group organized? So let's make this. And this goes back, funny enough, to the beginning of the class. You guys remember this? The concept of set of numbers? Concept of set of numbers? You guys remember? Finite set? Something like 1, 2, 3. Okay, that's a finite set, right? That's a finite set, right? What if I have something like 1, 2, dot, dot, dot? That's countable, but not finite. Okay, countable, but not finite. Okay, what if I want to give continuous number? Okay, from 0 to 1. This is also infinite, right? But it's bounded. It doesn't go all the way to 5. It doesn't even get to 2. But within here, how many numbers can you have? How many numbers can you fit? Infinite. Okay. So finite, infinite, but countable. Infinite cannot be counted, but bounded. And then you have this. Unbounded. And then you have this. Okay. This is a set of numbers. Okay. There are 5 types of five types. Okay. Now, if I'm going to start with 1, 2, 3, I can start with 7, 8, 9. But let's say if I start with 7, 8, 9, I don't stop. It's the same thing as this, roughly, right? It's just countable, but not infinite. So finite, there are so many elements. Countably infinite, infinite, but you can count 1, 2, 3, 4, 5. You just can't stop. Infinite, but bounded on both sides. Okay. Cannot go to the left of this, cannot go to the right of that. But there are infinitely many numbers squeezed in there. This here is unbounded, but it's unbounded on one side. It's called semi-bounded. This is the set of number. What's that got to do with probability? Aha. Remember I told you guys the axis here is the possibility. And the possibility comes in 5 versions. Finite possibility, like just now, Bernoulli, right? If I toss the coin 7 times, what is my possibility? 0, 1, 2, 3, 4, 5, 6, 7. Finite. Okay. So Bernoulli binomial is like this. Bernoulli and binomial. Okay. Bernoulli is a special case of binomial. Okay. This thing, you don't know yet. You don't know an example. I'll give you just the name. And I told you that these are the names that if you know and you study in your share screen and go to Wikipedia. Bernoulli, okay. Again, Bernoulli is just one of them. Now watch this. With finite support. Finite support. Okay. Finite support, but discrete. Okay, that's the key word here. The key word is if it's discrete, the probability is concentrated at a point. Okay. In other words, it's one of these spiky things. Okay. Now, if it's finite, that means you know what the minimum is and you know what the maximum is, and it can't be beyond that. So if I toss the coin 78 times, how many values can I have? 79, right? From 0, 1, 2, 3, up to 78. So this is can be as big as you want, but it has to be finite. So that's why you have this Bernoulli binomial. Okay. Again, Bernoulli and binomial are related. Bernoulli is the name of the guy. Binomial is when you have Bernoulli many times. Okay. Fine. With infinite support, that's like 1, 2, 3, 4, 5, 6, 7, 8, but you can't stop. Okay. There's no upper bound. The one that you need to know, okay, sometimes negative binomial is useful, but the one that's most useful is Poisson. Okay, it's the name of the guy. Say it's the name of the guy. For example, this could be counting number of accidents in an operation in your company. Okay. It doesn't mean that you're going to have accident 1,000 times. It just means that you cannot have a definite upper bound. Because if you had 5 accidents, you can always have 6. If you have 1,000, you can have 1,001. So there's no upper bound. It doesn't mean it's likely. Okay. Otherwise you go out of business. So that's Poisson. So you have to know this guy. Now, this guy, this guy. This one on the bounded interval, but continuous. Continuous means it's not at a point, right? It's continuous number. So if it's bounded on both sides, the most that you will see is a uniform. Uniform, okay? And that one, if I say random, variate, open bracket, uniform 1000, it's exactly the same thing as typing in RAND open bracket, close bracket in Excel 1000 times. Exact same thing. Okay, it's generating uniform between 0 and 1. But sometimes it's between 0 and 1, but not uniform. And that's the generalization of uniform called beta. Beta. Okay, what we got so far? Let's count Bernoulli too. So that 1, 2, 3, 4, 5. Five more. Now, just as I showed you earlier, there's unbounded, but bounded on one side. Okay, that would be something like lifetime. In other words, how long is this machine going to last? It cannot last negative time because it's still working. So it has to be positive. So it doesn't start negative. It started 0. So you bought something, it can break down right away. Or it can break down in a million years. Okay, in engineering, that happens a lot. Okay, obviously the probability certainly dies down. And one of the most useful is called exponential. Okay, I'm just gonna do hand waving because it looks like this. Okay, it looks like this. Now, think of the machine breaking down. Yeah, this could be a good way of modeling, predicting when it's going to break down, right? Again, predicting is about telling the probability. So it has this probability of breaking down between year 1 and year 5. Okay, so if you knew this, you can do a warranty, right? Now, most things are not going to be likely to break down right away. So sometimes it will be something like this. It will have a start, a hump. So it's kind of like it's not likely to break down right away, but maybe around year 5 or so. In order to allow for this, exponential doesn't do it. Gamma can do it. Okay? And all of this, by the way, is and more. Mathematica has the largest probability distribution library of all the platforms in the world. So obviously it has all this basic. So 1, 2, 3, 4, 5, 6, 7. Okay. Now, this one starts from 0. But what if something can go negative, like stock return? The most usual one you see is the normal. Okay. Another one, I'm just going to give you the name. Okay. It's called students T. Okay. So how many we got so far? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Right. And one more, but I'm not gonna talk about it. But I could, yeah. Just stop at 9. There's one Erlang. There's. Let's just say that here there are really weird events like probability of earthquake or something, very extreme value. That's kind of like another group of probability. So I kind of like call that maybe group 10. But as far as your livelihood goes, okay, whatever distribution you see in life, whatever data you see in life, if you know 1, 2, by the way, I'm just going to cross out Bernoulli because Bernoulli is like binomial. Okay. So in your shopping list, if you have, I'm going to cross this as well. Exponential is a little bit like a special case of gamma. Uniform is a special case of beta. So even though I told you that 10 of them, right? Actually, it's less. Okay. Now, if you have binomial, beta, Poisson, gamma, normal, student 3, you're okay. That covers all the situation in life. In fact, like I told you, right? Even if Mathematica gave you the best solution is here, chances are I'm going to try to explain my data in terms of what people understand, which is gamma. Okay, so ultimately, and you can do this in Mathematica as well, and say, instead of finding distribution in general, find distribution among the list that my clients are familiar with. Let's say my clients is familiar with gamma, but also familiar with Pareto. Okay, I would say, okay, try gamma and Pareto, but don't try everything. Just try these, okay? Try these, because these are the ones that my clients understand, okay? But for your career, and this is obviously not going to apply digital intelligence in anything. Binomial, beta, binomial, Poisson, beta, gamma, student T, and normal distribution. So one of each, but 2 in here. Okay, 2 in here. There's actually logistic as well, but this is only useful for people working in financial market. Financial market in Thailand is a little bit like this. Okay, and also in Thai market, it's also this guy. Where's that one? Koshi, this one. Okay, this just happens to be if you're in a financial professional, then they'll know these 2 more as well. Okay, but forget it. Okay, so binomial, finite, infinite, Poisson, doubly bounded or bounded, beta, semi-bounded, gamma, unbounded, normal, and students T. So basically 6, okay, 6. Again, if you're a financial professional, you're expected to know a few more. So what exactly do you do with this? Well, that's it. In reality, even though Mathematica can give you the best fit, you sort of like have to narrow down first. Okay. And because I just told you that for each of the support, for each of the kind of data, there's only one that you need to choose. So chances are, if you see something that's finite, you try to fit it with binomial, right? If it's countably infinite, you would try to fit it with Poisson. If it's bounded, now bounded from 0 to 1 is the same thing as bounded from 7 to 11. You just stretch the value, right? If it's doubly bounded, you use beta. If it's bounded on one side, you use gamma. If it's unbounded, then you have normal and student T. Okay, so that's in reality, you are just choosing this and then have the computer come up with the parameters. So that's what probabilistic modeling is. Now, again, why does it make it to this interactive class? Because you know, with this Mathematica tools thing, you can play around with fitting. It's almost like you can use a histogram, right, and draw a picture on top of it and move the buttons until you get the best fit. You can do that as well, except, you know, it's better to have machine do it. So once you get the data, it would tell you that, well, it has Poisson distribution with parameter, blah, blah, blah. Now, what does each mean? Then you have to go to the Wikipedia page and try to explain it away. For example, let's say, in this case, Poisson. Okay. So you explain the shape, and you also explain in terms of basic statistics. Mean would be like where the middle is. Okay, and this is, I think, very elementary. Mean, median, mode. You guys know about this, right? Standard deviation. Yeah? Do you not know? Okay. So these are basically what the word statistics come from. Is the statistics of the distribution. So this is the shape. The way I taught, you know, I've taught, like, you know, MBA statistics. The way I teach MBA statistics is to do this. You go out, you do market research, you get this histogram, right? You get this histogram, you cannot fax, and this is analogy I use for MBA student. If I can send the function, I'm done. I cannot send the function. So what do? I send the name of the function and basic description like the mean and standard deviation. So in normal case, in normal distribution, it happens that if I happen to see my data looks like this, okay, what I would tell my team, say, okay, this is something, it's the size of something, okay? It's the size of shirt, let's say, okay? Oh, that's a good one. Let's say I want to sell pants, okay? And I go to a different country, and I go into a country that people are a lot fatter in Thailand than in Thailand. So most of the guys have 40-inch waist. Most of the guys have 40-inch waist, right? And then about 68% of them fall within this, say, 50-inch and 30-inch waist. In order for me to communicate this, what I would do is I designate this shape as normal. I designate the middle as 40. So I don't have a fax machine, but I have a telegram. So I send N, open 40, comma 10. Okay. This is how I specify the whole shape. N is the name, and that has its own function that, you know, my team can look up. The point is, this is how I specify, and I say that 68% of the people have this waist size. So, you know, you can make small, medium, large, I guess. Now, technically, is this correct? Is this correct? Anybody? Technically, this cannot be correct. Why not? Because normal distribution go to minus infinity, right? But for practical purpose, this probability goes to 0 very quickly, okay? This is what means by practical assumption. Practical assumption doesn't mean no math. Practical assumption means you're willing to allow for a little bit of negative infinity and positive infinity here and there, as long as you can analyze 99.9% of the data. Okay, so technically, if people have this waistline, there are actually people with negative waistline, negative infinity waistline, positive infinity waistline. But as long as by drawing this, you know, it allows me to analyze 99.999% of my clients, I'm okay. I'm okay. I can live with that. That's practical assumption. Okay. Practical assumption, again, doesn't mean no math. It just means even though the math allow for like positive infinity, it doesn't bother you. Okay. So that's how you would do it. Now, what do statisticians do for the rest of their lives? They have to do with these parameters. One guy's job is to estimate 40 and 10. The other guy's job is to test. If I say it's 40, should I believe it? That's called hypothesis testing. Okay, so statisticians are kind of like in a sort of like they have a separation of tasks. One guy's job is to come up with a parameter that's called estimation or estimator. The other guy is to say, well, I claim that these people have 68% between 30 and 50-inch waist. Is this statement true? And the other guy tested. That's called hypothesis testing. In real life, it's the same guy. Same guy, okay, just statistician. What would happen is the second one has a meaning in law. For example, if I want to say, and this is a practical example would be I claim average, okay, so this is average pollutant from my factory is 7 molecules in part in million, okay, and I claim that it's sort of like plus minus 2. Okay, that's my claim. That's my factory. I claim. I send this, and let's say this is legal, but not beyond this. So the regulatory agency, EPA, Environment Protection Agency, comes in and take all the data and say that this is not true. Your factory actually emits this distribution of bad stuff into the environment. Okay, so that's what statisticians do in life, in court. That's how companies get fined or regulated for breaching environmental law and so forth. It's all done with statistics. Okay, and most of the statistics in law, that most of the distribution that you would see in law or in real life is normal distribution. Okay, that's why I circled it. Okay. Now, so okay, so that's what I kind of planned for today. Sorry, it took a little bit too long, so didn't get to bring the guide. So on Wednesday, I'm just gonna make it like, instead of like an hour too long quiz test, I just have a little quiz so that I can have some of you show. Okay, hopefully you will have what we did last time, the exercise where you bring in your demonstration like the girl did. Okay, yeah. So again, look back at your demonstration, Mathematica demonstration program, the one that you pick. I'll just randomly pick some of you and we'll discuss it. Okay, like I said, last time the girl was picking about the program that draws a torus, right? And I elaborated on what a torus means, geometrically as well as mathematically. Yeah, it should be the one that the first week I asked you to, yeah. But you can change your mind. You can choose something else that's more interesting. Okay, a lot of them, if you go to Mathematica, well, demonstration, yeah, a lot of them will have this distribution flavor. In other words, the things that they show is in, yeah, especially in social science business, there's a lot of probability in here. That's a lot of example. So, for example, business, economic, finance, all this, we have a lot of probability model. Okay, so it's not X is something and Y is something else. It's X and probability of X. So this, for example, this is about probability. This probability. This definitely is, well, I don't know what this is. Yeah, but certainly probability distribution come up a lot. Probability distribution. Okay. Now, see, you can right away. I can eyeball you and tell that this is based on binomial distribution. This is based on normal distribution. Okay. Because again, normal distribution is so useful. เรียกว่าเป็นของหากิน. Let's put that way. Okay. So I told you the 6 of them, right? Now, the reason that the last one, normal, is not good enough is because in real life, students T happens a lot. Happens in financial market. What it means is that it's a lot less sure. It's more spready. It's more spready. Okay. And that's where the risky part comes in. Okay. You kind of think that, yeah, it's kind of here, but no matter how you draw it, it's very spready. It's called heavy tail distribution. And that's why the student T, that's why for the unbounded, I didn't give you just one. I say normal and students T. Okay. So that's that. See, What's this guy? Bernoulli, right? What's this guy, by the way? I can tell you right away, this is probably something that had to do with gamma. Something similar. Negative binomial, I haven't covered, but that's also a useful one. So to be fair, let me rephrase finally. When I say that there are 10 distributions in life that you should learn, 5 of them are like special case of the other. So there are about 6 of them that you should learn. But if you're a financial professional, if you're working with marketing research, if you're working with something, chances are in each of those fields, you would have to know a few more that are very common in that area. Okay, so if you're a financial professional, you certainly will have to know logistic distribution as well, something like that. Okay, if you're in some kind of fraud detection, you have to know about benefit distribution, you know, a few more, but basically no more than 10. Okay, and that will get you throughout life, basically. Anything beyond that, 2 options. And this is the last thing I'm going to say today. 2 options. If you get something weirder than this, 2 things can happen. Number 1, you do what's called mixture. So maybe you mix the left half of a normal distribution with the right half of a gamma or something. I don't know. It's that kind of thing. So you mix and match things. Okay. That's one thing that can happen. The other thing is you go to the approach that doesn't have a name. And this would be under what's called non-parametric statistics, and also with machine learning. It's a little bit like that. Once you build a machine learning model, there isn't a name to it. Okay, it's a model you run on this data, but you can't say it is gamma, it is Weibull, it is Poisson. It doesn't have a name to it. It's specially tuned for the data. Okay, but for most of the time, the 5 will get you, it's the 6, not 5, the 6. Okay, once again, what? Once again, what you got? Binomial for this, for finite, Poisson for countably infinite, beta for bounded 0 to 1, gamma for semi-bounded 0 to infinity, and then normal or student's t for unbounded, minus infinity to plus infinity. Okay, and in real life, even if what you're working with cannot have negative infinity, sometimes you would use normal. Okay, so that's it. So that's all I've got to plan. Hopefully that this is give you enough intuition to see that, you know, with interactive tools like Mathematica, you can play with. You can play with from anything, linear algebra, calculus, and now probability. So those are the 3 things. You will learn the nitty-gritty details in that, but the way I suggest is, as you learn those, you can do interactive display, you know, on the side, so you can see how the parameters work. Okay, so I'll see you on Wednesday. Might have to spread you out so you can take the test or whatever. Okay, I'll make it just a quiz so that doesn't take too long.